Hello everyone, this is Shimon Yu from Georgia Tech. Today is my great pleasure to give this tutorial at International Memory Workshop. The topic today is ferroelectric field effect transistor, FeFET, and we're going to discuss recent progress in the 3D integration, including the back-end line integration and 3D vertical line structure of the FeFET. And also we will talk about the multi-bit feature of the FeFET used in the neural network as synaptic devices. Here is an outline of the presentation. First, we will give a brief introduction to FeFET, and then we will survey the fundamentals of FeFET, including the minor loop switching dynamics, array level operation, variability, and scalability. And then we will give a brief introduction to computing memory as a paradigm for the neural network acceleration. And then we will talk about 3 applications of FeFET for computing memory. Let's first review the basics of the polarization and ferroelectricity. Polarization is defined as the sum of the dipole moments in dielectrics. So in the normal dielectrics, the dipole directions are randomized after the electric field is removed. But in the ferroelectric material, the dipole directions are aligned with the electric field and they are remained after the electric field is removed. Therefore, there will be the remnant polarization. Today's CMOS-compatible ferroelectric materials that are of interest are mostly the doped hafnium oxide. For example, hafnium Z-choline oxide, HZO. The symmetry of the hafnium oxide crystal structure is broken by the doping. Therefore, we can create this dipole polarized up and down. The typical hysteresis loop in the ferroelectric materials is shown here. We have the polarization versus the voltage. We can polarize up the device by positive voltage and then polarize down the device by the negative voltage. So here we have the remnant polarization defined as a PR, and this is like a memory window. When the ferroelectric material is integrated in the gate stack of a transistor, it becomes a FeFET. So here we are going to review the fundamentals of the FeFET. If we want to program the FeFET, we can apply positive gate voltage that is large enough. The ferroelectric materials can be polarized down, and then the positive charge near the interface between the gate dielectric and the channel can induce the channel inversion more easily. Therefore, the threshold voltage will be decreased after the programming operation. Here the IV sweep of the FeFET is shown after the programming. Then the current is increased and the threshold voltage is effectively reduced. If we want to erase the FeFET, then we need to apply a large enough negative voltage to the gate. Then the ferroelectric material is polarized up and the threshold voltage will effectively increase. Then the device will have very low currents. So the channel conductance effectively can be modulated by the polarization in the gate dielectric with multi-level states. Therefore, the FeFET is suitable to map the multi-bit weight in the deep neural network. Here, the FeFET holds many advantages over the regular flash memory, which also based on the modulation of the threshold voltage by the charge trapping. But the FeFET has much lower write voltage, around 3 volts compared to more than 20 volts in flash. And also, FeFET has much shorter write latency, about like 50 nanoseconds compared to more than like tens of microseconds in flash. FeFET also holds many advantages over other resistive non-volatile memories, such as RAM or phase change memory. This is because FeFET has much lower write energy less than 10 femtojoule per bit because of the field-driven mechanism instead of the current-driven mechanism in the R1 or phase change material. The FeFET concept was initially proposed with a conventional perovskite ferroelectric material such as the PZT or SBT, but those conventional FeFETs were not scalable because of the thin film thickness of the PZT or SBT can be as thick as hundreds of nanometers. Therefore, it's not compatible with the advanced CMOS technology node. The recent discovery of home-bake phase of hafnium oxide enables the scalability of the FeFET towards advanced CMOS node. So here we review the state-of-the-art research and development results from the industry in the past few years. For example, GlobalFoundries demonstrated a 28 nanometer high-k metal gate bulk FeFET in IDM 2016, and then a follow-up work on the 22 nanometer FTSOI FeFET on the IDM 17. And also IMEC demonstrated a 4-layer vertical FeFET based 3D NAND structure. So here the FeFET are integrated as sidewall of the trench. And in the last year's IDM, Intel reported a backgate FeFET, which shows much improved endurance up to 10 to power 12 cycles. Next, we are going to present the research progress on the fundamentals of FeFET. The first one is the minor loop switching dynamics, which result in a history effect. So what is the history effect in the minor loop switching? Let's look at one example from the ferroelectric capacitor, FeCap. So if we use a precise model to do the simulation of the minor loops, we can have the following results. Let's assume the waveform applied to the capacitor following those two kinds of trajectory. So the small loop starts from S0 state, and then it will go up and then come down to the S2 state in this polarization versus voltage PE curve. And then the large loop will start from the same S0 state, but then it will be polarized to a larger S3 state. And then the S3 state, if we apply negative voltage, then it will come down to the S2 state. Now here we have two possible transitions from the S2 state back to the S1 state. But if we follow the small loop, the red curve, then the voltage to change from the S2 state to S1 state is the voltage Vc. And then if we follow the large loop, then the voltage to switch from the S2 to S1 will be this voltage Vd. And then we can say that the voltage Vc and Vd does not equal. So this depends on the history of the device, even though we have the same transition from the S2 to S1 state. And then we experimentally validate this kind of history effect by using the FeCap devices. And here we show several samples with different kinds of waveform trajectory. And here you can see that the voltage indeed to switch from the S2 to S1 state will vary, depends on the prior path it has gone through. So here, for example, the smaller loop use negative 1.19 volts to switch, but the larger loop need to use negative 1.5 volts to switch. Similarly, you can see the voltage is different in other examples. We also validated the history effect in different measurement setup. For example, here if we change the sweeping polarity to the positive side, we also see that the different loops may result in different switching voltage even from the same transition from those two intermediate states. and we have seen this kind of trend in different samples. And also, if we change the sweeping frequency of the triangular waveform here, if we increase the frequency, then we can see this kind of PE curve. But again, the voltage to switch between those two states vary, depends on the prior path the device has gone through. So we would argue that the history effect is universal in the FE cap. Not only FE cap, but also FeFET shows the history effect. So here we experimentally validate the minor loop switching on GlobalFoundries 28nm high-k metal gate FeFET samples. So here we first consider a large loop, and we first program the device to the G3 state, and then we reset the device to the G2 state, and then we reset to the G1 state. So here we use negative 2.8 volts on the gate to reset from S2 to S1 state. But if we consider a small loop where we directly change from the S2 to S1 state, even though the conductance change is similar, but the voltage we require to change will be different. So here we only need negative 2.5 volts to change from the S2 to S1 state compared to the larger loop where we have gone through the S3 state. And we can consider a different minor loop where we start from the same S2 state, but if we keep using the same voltage, let's say negative 2.8 volts, then we are going to result in a much more reset state. This one, the conductance will be like 11.2 nanosiemens, but previously it's only 0.19 microsiemens. So here we can validate similar minor loop in different samples. I will skip the details of the other samples, but again, this kind of history effect is universal in FeFET as well. So what causes the history effect? Here we use the phase field modeling to simulate the multi-domain switching considering the variations in the coercive field of each individual domain. And we use this time-dependent Landau-Ginzburg framework to simulate the evolution of the domain polarization switching as follows. First, we consider the larger loop where the device has gone through the S3 state, and then S2, S1. The minor loop will directly switch from the S2 to S1. If you compare the two loops on the same state, S2, they have similar average polarization value, about 0.6, but the internal domain configuration is different. Later, when we switch to the S1 state, which also have similarly average value, about 0.6, but the internal configuration again is different, and the voltage or the electric field to switch from the S2 to S1 is different in this larger loop versus this minor loop. This agrees with the experimental data we have shown earlier. I'd like to give you a more intuitive understanding what's going on here. We can use this cartoon figure to show the different coercive field of the multi-domain in the device, where we call the domains with larger coercive field as hard domain, and the domains with smaller electric field as easy domain. So in the larger loop, the device has gone through the S3 state, where most of the hard domains have been flipped down. Later, if we want to change from the S2 to S1 state, then we have to flip those harder domains. That means we have to use larger electric field. In the minor loop, even though at the S2 state, the number of domains flipping up and down will be the same, but those domains mostly are the easy domains. So later, when you switch from the S2 to S1, you just need to flip those easy domains. Therefore, the electric field to flip the domains will be smaller. So we can understand the history effect using this chart. So the history effect may negatively impact the neural network training accuracy. This is because if we switch between the intermediate states, it's really hard to track the device's history. Therefore, it's almost impossible to design the voltage to accurately tune the device to the target conductance states. Therefore, we result in the error in the weight updates. To quantify this kind of effects, we built a compact model incorporated into the neural network training flow, as shown here. And then we use MNIST dataset as a recognition task to test the training accuracy. And we see that only 91% accuracy can be achieved if we consider the history effects of the weight updates. To mitigate this problem, we propose a new protocol that is to always erase the device to the ground state before the next programming. Therefore, the device will always operate along the saturation loop. If you do this fully erase before program, then we can say that the training accuracy can be recovered to the 97%, which is close to the software baseline. Of course, the overhead of this new programming protocol is additional erase pulse, which means longer latency and larger energy. Next, we're going to discuss the array-level operation of the FeFET. In particular, we're going to propose a drain erase scheme. This is required to enable the random access that is important to the weight update in the deep neural network, because sometimes we need to increase the conductance and sometimes we need to decrease the conductance depending on the weight update rule. So here is a proposed programming and erase scheme to enable the individual cells weight update in the FeFET array. And here we can see that we use the gate to program the device, where we apply 3 volts to the word line, and then we ground the source line and bit line. So the device will receive a positive potential drop across the gate stack. So this will program the device. And in the erase, we are going to ground the gate by applying 0 to the word line, and then we raise the potential of the bit line to be 3 volts and the source line to be 1.5 volts. So effectively, from the drain to the gate, we will have a negative 3 volts. Then we can effectively erase the device. We need to examine the possibility of the drain erase in the next slide. We characterize the drain erase scheme on GlobalFoundries 28nm high-K metal gate FeFET and 22nm FDSOI FeFET. So here this is a waveform we applied. We are going to bias the source to be 1.5 volts or 0, and then we will apply the drain pulse. So here, as we increase the drain pulse amplitude from 1 volt to 3 volts, we can see that the drain current effectively decreases. That means the erase is successful when we increase the voltage to 3 volts. And here is a bias condition again. The gate is grounded and the drain voltage raised up to 3 volts. The erase is successful. And then we can vary the pulse amplitude and pulse width to draw this kind of 2D phase map to show the erase is successful from the initial 1.1 micron M to the eventual 0.14 nanoM. So we achieve 4 orders of magnitude on-off ratio by varying the pulse width and pulse amplitude. But also we can see other testing conditions. For example, if the source is grounded, then the on-off ratio is not very large. That means we have to increase the source to be half bias, 1.5 volts. And also we can examine different device W over L. The drain erase scheme is also effective. And then the last one is the high-K metal gate bulk devices. Unfortunately, the drain erase is not very successful in this bulk device compared to the FDSOI device. The reason is that the FDSOI has a confined channel, so the drain voltage can effectively raise the channel potential. Therefore, we can have negative voltage drop across the gate stack to enable the drain erase. The drain erase is effective to the selected cell, but also we need to consider the inhibition to the unselected cell in the array. So here, for example, if we have the drain voltage applied to the unselected cell, then we need to apply gate voltage to inhibit the cell from being erased. And here we experimentally validated the inhibition condition. For example, if we bias the gate to be half of the drain voltage, then we can say that the transistor still maintain large drain current. That means the device is not erased. And we repeated this kind of inhibition condition for many erase cycles up to 10 to the power 6. Still, the current maintains high. That means the inhibition is successful. Next, we will address the variability and scalability of the FeFET from a TCAD perspective. Ferroelectric devices may show significant variation. For example, the dispersion in the IDVG curve of a FeFET. The primary reason of the variation is this phase variation of the ferroelectric polycrystalline thin film. And the image here shows a measured phase map, consists of a mixed monoclinic phase and orthorhombic phase. As the active device area scales, the variation tends to become more significant. In order to evaluate the impact of the phase variation on the FeFET behaviors, we here present a modeling methodology using a Voronoi diagram. So this is the flow to generate the phase map in the ferroelectric devices. And we're going to incorporate this kind of mixed phase map into the gate dielectric in the TCAD simulation. In this particular example, we show the ferroelectric phase versus the dielectric phase probability around 70% to 30%, and the average grain size is about 7 nanometer. With this approach, we can model the variability as we scale the FeFET technology node. So here we show 3 TCAD structures. First one is a bulk transistor structure at 28 nanometer. Second is a FDSOI structure at 22 nanometer. And then the FinFET structure at 14 and 7 nanometer. So here we are going to apply the mixed phase patterns for the active Fe layer. Here we show the simulation results from 100 Monte Carlo runs of the TCAD simulations. Here we show the memory window statistics of different structures. The first conclusion here is that the memory window actually increases with the scaling, especially from the planar structure to the FinFET structure. This is due to better gate-to-channel coupling. Second, we notice that the variation of the memory window actually decreases when we switch from the planar structure to the FinFET. This is because the FinFET actually has more active Fe layer area because of the sidewall. Therefore, the variations impact is mitigated. Next, we are going to discuss the applications of FeFET towards the computing memory paradigm, especially for the neural network acceleration. Here are the motivations to develop the specialized hardware accelerators for artificial intelligence or machine learning workloads. As we know, GPU is still dominating the training in the cloud, and we see that FPGA is becoming a popular platform for the inference, especially for fast prototyping. And also, there's a new trend to develop the digital ASIC platforms, for example, the
Google's TPU to perform the accelerations at the cloud as well as the edge. So if you look at the different computing platforms, the energy efficiency varies or not. So here the energy efficiency is using the metric tera operations per second per watt, or TOPS per watt. And the conventional computing platforms like GPU is about 0.1 TOPS per watt, but it can support the floating point computation. And the digital ASIC platforms like TPU or the equivalents can achieve like 1 to 10 TOPS per watt. But it can support the fixed point computation. If we want to further increase the energy efficiency to like 10 to 100 TOPS per watt, we believe that computing memory technology is a promising paradigm. So here we are going to use the analog computation within the memory array. The memory can be CMOS, like SRAM, or the emerging non-volatile memories. And then we have to embrace the low precision computation. And then the question is, can we achieve the same accuracy as the digital platforms? We are going to discuss those issues in the presentations today. The key idea of computing memory is to use the crossbar array to accelerate the weighted sum and weight update process in the neural network model. So here we show an example of the one-layer network to be mapped to the crossbar array. So here the weight of the network is mapped to the conductance of the memory devices. And then the input vector x is mapped as voltage to enable multiple rows. And then the voltage multiplied by the conductance of the device will result in the current to be summed up along the columns. And then the output will represent the weighted sum. We may need to use the analog to digital converter, the ADC, in the peripheral circuits to digitize the analog output. But we can do this process in parallel, so we can speed up the vector matrix multiplication. This is for the inference stage of the neural network model. And if we want to train the neural network, that means we have to update the device's conductance frequently by using the pulsing skin, which is determined by the learning rule. And we can translate the delta W to be the number of pulses to be applied to the device. There are several kinds of emerging non-volatile memory that can be engineered towards the resistive synaptic devices to be used in the crossbar array. And here we show the examples of the filamentary R1, where we form the conductive filament in the oxide material. And generally, in this kind of filamentary R1, the set process is abrupt. That means it's hard to achieve multi-level states, which is typically required in the synaptic applications. The second candidate is a non-filamentary R1. In this case, we rely on the diffusion of the defects between two kinds of oxide layer. Typically, this kind of non-filamentary switching is slow, and the retention may be poor. The third candidate is the phase-changing memory, where we can switch the crystalline phase and the amorphous phase by the heat pulse. And in this case, the reset will be abrupt because we have to melt this material and then go through the quench process. And the last candidate is the ferroelectric field effect transistor, FeFET. So in this case, we replace the gate oxide with a ferroelectric layer, and then we can partially flip the domains in the ferroelectric layer, so we can fine-tune the threshold voltage of the transistor, where the conductance of the channel can represent the weight. So in this case, we have better control of the weight tuning by the gate pulse, and then the read and write paths are decoupled, so then the reliability may be improved. And we will see that in today's talk, the FeFET is a suitable candidate for the resistive device. Here's a wish list for the ideal synaptic device. First, we want the device to be as small as possible, less than 10 nanometer in dimension. Second, we want the device programming voltage to be compatible with the logic power supply, about 1 volt. Third, we wish the device have multi-level states, let's say larger than 64 states, or equivalently 6 bits. This is required for the training. And also, we prefer the device to have linear and symmetric updates to achieve good training accuracy. And this requirement can be relaxed to be 2 bits, 4 levels for inference. And then the device dynamic range or on-off ratio should be larger, let's say 100. And then the device on-state resistance preferred to be in the range of 100 kilo ohm to 1 mega ohm to minimize the read dynamic energy and maintain reasonable readout speed. The device energy consumption for the programming should be less than 10 femtojoule per pulse. And then device retention should be good, larger than years for inference. And then the device endurance should be larger than 10 to the power 6 updates for the training. Of course, all of those numbers here are application dependent. That means we have to consider the problem size, the data set, and so on. We want to claim that the ferroelectric transistor FeFET can meet most of the requirements in the previous slide, probably except the programming voltage. Here we want to show a pioneering work by my collaborator, Professor Sumandata's group at the University of Notre Dame. So here they published the first analog synapse based on the FeFET in the IEDM 2017. So here the transistor is a non-channel transistor based on the HZO gate stack. The hafnium zirconium oxide is a well-known ferroelectric material and which is CMOS compatible. So in this case, we can use the pulse to the gate to partially polarize the HZO thin film. Then we can result in different threshold voltage in the transistor's transfer curve. Here you can see that at the fixed gate read voltage, then we can have different conductance read out from the channel. Then we can use this conductance to represent the analog weight in the synaptic device. Using this device, we demonstrate the symmetric and fast weight update. As you can see here, we apply the pulsing scheme with varying pulse amplitude, but with 75 nanosecond pulse. So we can potentiate the device's conductance following this trajectory, and then we can depress the conductance following this trajectory. So it's quite symmetric respect to the potentiation and depression. And in total, we can achieve like 32 states, that means 5 bits, in this FeFET device. And then this right-hand side shows the IDVG curve of the corresponding multi-level states, and you see the gradually changed threshold voltage.
Next, we will present 3 designs using the FeFET. The first one is to utilize the back-of-line compatible FeFET for the deep neural network inference. The motivation of building FeFET at the back end of line are as follows. First, it can save the bit cell area due to the 3D folding. Second, we can use the backgate topology with the oxide channel. This can effectively remove the interfacial layer between the channel and the gate dielectric. Therefore, it can greatly improve the reliability of the FeFET. For example, the defect generation at the interface can be minimized. Certainly, the oxide channel typically has lower mobility. This will increase the channel resistance. This is especially attractive for the computing memory because we need to parallelly turn on multiple cells. Higher channel resistance will help to reduce the readout current. Therefore, the energy efficiency can be boosted. In the recent IEDM, Professor Sumandata's group from University of Notre Dame demonstrated a 3D two-tier FeFET design. So the FeFET is built on top of a front-end CMOS transistor, and the backend of non-FeFET utilizes an oxide channel. In this particular case, it's the indium tungsten oxide. And then the HZO ferroelectric layer is deposited between the backgates and the oxide channel. The short channel behavior as short as 20 nanometer gate lengths have been demonstrated in this work. The characteristics of this back-of-line FeFET are summarized in this slide. First, the IV hysteresis is shown here after positive and negative 5 volts program erase. The distinguishable memory window is shown here. Second, the endurance cycling is performed over 10 to the power 8 cycles. The memory window is well maintained after the cycling with 5 volts and 1 microsecond pulse width. Lastly, the data retention is reasonable. After 10 to the power 3 seconds, the memory window is still distinguishable at room temperature. Multi-level cell operation is also possible with this back-of-line FeFET. So here we show 2 bit per cell demonstration. By using different programming voltage, we can program the cell into different conductance states. And in this case, we show a very tightened distribution of 4 levels of conductance states. Here, I'd like to point out that to enable the computing memory, we need to use this pseudo-crossbar array architecture, where a regular transistor is used as a selector to control the gate of the FeFET. The reason is that we need to cut off the current if the input data represents 0. This is because the FeFET, after the programming, will have a negative threshold voltage. If we don't have the selection transistor, then even the input is 0, then the FeFET, if it's programmed, it will also contribute the current. But ideally, we know that with the input 0, then the output should also contribute negligible current. Therefore, we need to use a regular transistor to cut off the current that is from a fully programmed FeFET cell. To summarize here, we need 1 regular transistor and 1 FeFET. Therefore, the 3D folded back-of-line FeFET bit cell is perfectly suitable for this application. Lastly, we show a benchmark at the system level to review the benefits of using the FeFET, especially back-of-line FeFET, for the neural network acceleration. So here we utilize an open source tool called DNN plus NeuralSyn, which is available at this GitHub link. So the benchmark is done for a VG8 network for CIFAR10 datasets. And we compare different technology implementations of the neural network for the computing in memory architecture. And here we have different non-volatile memories at 22 nanometer and also SRAM at 7 nanometer. As you can see here, the FeFET, especially the back-of-line FeFET, has a much higher on-state resistance. This is because of the reduced mobility of the oxide channel. Therefore, the energy efficiency of the back-of-line FeFET implementation is much better because the energy here is dominated by the readout current from the memory array. And also, if you compare the FeFET back-of-line versus the conventional FeFET at the front end of the line, because of the 3D folding, the chip area is also greatly reduced. So here we can conclude that the 22 nanometer 3D backnova line-folded FeFET implementation can outperform all other competing technologies, even the SRAM at 7 nanometer node, in terms of the energy efficiency and chip area. So far, we talked about the inference of the neural network. Next, we are going to introduce how to use the FeFET for the in situ training of the neural network. In this particular case, we will introduce the concept of the hybrid synapse. The hybrid synapse was motivated by the hybrid precision for the training versus the inference. So here we see an example of the very simple neural network for the MNIST recognition. So here you can see that for the inference, like 1 or 2 bits can be sufficient to guarantee the accuracy. But for the training, we need at least 6 bits of the weight to achieve good accuracy. Therefore, the key idea is to use the non-volatile memory to store the most significant bits, while using the volatile memory to store the least significant bits. For example, 6-bit weight is represented by 2 bits in the non-volatile memory and 4 bits in the volatile memory in this example, a capacitor. Therefore, the non-volatile memory stored weight can be used for the inference, while the frequent updates can be accumulated in the volatile memory, like the capacitor. The hybrid synapse consists of 2 regular transistors and 1 FeFET. So here the 2 regular transistors are responsible for charging and discharging the gate voltage of the FeFET. The gate voltage essentially represents the charges on the gate capacitor, which are volatile, but the gate voltage can be modulated in a fine and linear step. This can represent the LSB of the weight. But the MSB of the weight needs to be encoded as the different VTH states of the FeFET. So here we show 2 bits MSB. Therefore, we have 4 IV characteristics in this plot with different VTH. The gate voltage is maintained between the VA and VB 2 points. Once in a while, if the gate voltage is keep charging beyond the VB point, it will generate a weight transfer step to change the state from S0 to S1. This effectively represents programming the MSB of the weight. So the MSB step is coarse, but is non-volatile. So after the training is done, then the only MSB states are remained. Therefore, we can use that for the following inference. To demonstrate the effectiveness of using this hybrid synapse, we simulated this 2T1 FeFET bit cell weight update behavior using the FeFET compact model with the transistor model in SPICE. And here we show the equivalent conductance tuning curve, the conductance increase and conductance decrease. As you can see here, is quite linear and symmetric between the positive weight update and the negative weight updates. And the 64 states are equivalently realized, representing 2-bit MSB plus 4-bit LSB. The symmetric weight update is very important to achieve the high training accuracy. As you see here in this neural network simulation, considering the linearity and the symmetry of the weight updates, you can see that if the weight update is asymmetric between the positive and negative weight updates, then the accuracy will quickly drop with increasing nonlinearity. So from the extracted behavior of this hybrid synapse, we found that the nonlinearity is symmetric with only 0.5 and 0.5 nonlinearity values for polarization and depression. So with this behavior, we can expect close to 90% accuracy for the CIFAR-10 dataset training. Therefore, this is very useful to achieve approaching software accuracy in the hardware in situ training. One potential problem for the hybrid synapse is the finite data retention as the gate node. So here we did the gate capacitor leakage analysis. The voltage decay should be slow enough. Therefore, the retention time of one-step LSB should be much longer than the time interval for the weight transfer. So here we assume 8 micrometer square FeFET gate area, and we use the 65 nanometer no power transistor model to simulate the leakage of this hybrid synapse. And the waveform here suggests that the retention time for one LSB step is about 1.64 milliseconds. But if we change the charging transistor to the oxide channel transistor, for example, the IWO transistor, as we discussed earlier, the leakage will be much suppressed to about 1 femtoamp per micrometer. Therefore, we can greatly reduce the gate area to only 0.014 micrometer square. And still, we can achieve very good data retention, about 320 milliseconds, if we have the IWO to function as the charging transistor. Lastly, we will discuss how to use the 3D NAND architecture with FeFET to implement a really large-scale neural network model. The deep neural network model tends to grow exponentially in terms of the number of parameters. The image classification model actually is relatively small, with only tens of megabytes weights. But the other applications, such as language translation model, could be as large as terabytes. Therefore, only 3D NAND architecture could reach such density. And here we propose to modify the 3D NAND architecture to support the in-memory computing as well. So the idea here is to enable one plane of the FeFET-based 3D NAND architecture. And then we use the SSL as the input voltage, and then measure the current from the bitline. Therefore, we can still map the neural network model to be one horizontal plane of the memory cells. And then we can use multiple blocks of the 3D architecture as the inputs, and then the current from the bitline can be sensed. Here we would like to discuss the voltage bias scheme for the weight programming in the 3D NAND. As discussed earlier, the drain erase will be useful to enable the random access to the array to program or erase individual cells. And here we show the 2D NAND program erase scheme first. So here the cell A is being programmed or erased, and the voltage biases to the program and erase are shown in the slide here. The 3D design has one unique feature, that is, we have multiple of those vertical slices in the 3D NAND architecture, and the word line is shared in the horizontal plane. Therefore, we have to differentiate the different strings from the different vertical slices. Therefore, the timing here needs to be carefully designed, because we only want to enable cell A in this case. So we have to first pre-charge the channel to be the half bias voltage, and then we need to turn off the SSL after the pre-charge. To validate the proposed program erase scheme, here we use the fitted FeFET model in a 3D NAND netlist to perform the HSpace transient simulation. So here, only cell A is being programmed or erased, and then we design the exact pulsing scheme using the timing diagram here to have the voltages applied to the SSL, unselected SSL, and the bit line and unselected bit line, as well as the word line and unselected word line. So here only the cell A will have enough voltage to program or erase. Then all the other cells like B, C, D, or the A prime, B prime, C prime, D prime will not have enough voltage to be programmed. Then we validated the 3D NAND operation for the inference as well, using the SPICE simulation. So here we activate the selected plane by the word line voltage, and then the input is going to activate multiple SSL, and then the readout current will be sensed from the bit lines. The unselected planes will be bypassed by the pass voltage. Inevitably, the unselected planes will contribute series resistance to the string. Therefore, the bit line current will be decreased, as shown in the simulation results here. As we further increase the number of layers, we are going to see a decrease of the readout current. Therefore, the limiting factor for the accuracy is the series channel resistance in the unselected planes. And we believe that at least 8-layer 3D NAND FeFET architecture seems feasible with sufficient accuracy for the readouts. Another challenge of using 3D NAND FeFET for in-memory computing is again the phase variation. So here we use a TCAD simulation to perform the analysis of the impact of phase variation of a 8-layer 3D NAND string. So here we statistically simulate 64 strings along the bit line, depending on the number of on-cells along the bit line. So when the number of on-cells is small, then the readout current is still distinguishable. But when the on-state cell along the bit line becomes large, then we see significant overlap between different readout current distribution of the on-cells. But fortunately, the neural network can tolerate such effect to some extent because we have the partial sum quantization effect. Therefore, we can use lower ADC precision to quantize the neural network. For example, here, 64 cells. Ideally, for the full precision, we may need 6 bits ADC, but if we only use 4-bit ADC, then we don't need to differentiate such overlapped distribution. We only need to distinguish between the cells on states 64 versus 60. Therefore, the overlap effects will be ignored. We realize that the 3D NAND fabrication may not be compatible with the advanced logic process. Therefore, we would like to leverage the hybrid bonding for the 3D integration of the computing memory architecture. This is similar to the CMOS under-array concept in today's 3D NAND flash, but the computing memory architecture has much more peripheral logic than the regular 3D NAND flash, because we have so many modules for the compute, including the ADC adders, shift registers, buffers, and so on. Therefore, we prefer to use the most advanced logic process to build those peripheral logic. Finally, let me summarize the presentation. So in this tutorial, we focused on the FeFET, and we believe it is a promising synaptic device candidate for the computing memory architecture. And the deep neural network in situ training requires high precision weights and linear symmetric updates. Therefore, we think the hybrid synapse consists of the 2 regular transistors and 1 FeFET is promising. To accurately tune the FeFET into multi-level states, an erase before programming scheme is usually necessary to avoid the history effect, as we discovered in the minor loop switching. The FeFET array requires individual cells to be increased and decreased during the weight update process. Therefore, the drain erase scheme is an effective method to enable the individual program and erase. Back-of-line integration of the FeFET on the top tier with the oxide channel transistor can improve the density of the bit cell and also improve the reliability of the FeFET, such as endurance. The variability due to the phase variation is still a concern, especially when we scale the FeFET to more advanced technology nodes. And the 3D NAND-like FeFET array is believed to be an ultimate solution for implementing large-scale neural network model up to terabytes. With this, I'd like to thank my research collaborators on the FeFET project, including Professor Suman Datta from University of Notre Dame, Professor Asif Khan from Georgia Tech. And then I'd like to thank the students and postdocs who spent their efforts in the research. Their names are listed here. Finally, I'd like to thank the sponsors of this research, including SRC JUMP program, especially as the Ascent Center under the JUMP program. The reference list for the cited research is shown here, and you are encouraged to read the individual papers if you are interested in a particular topic. Thank you for your attention.